Based on that, they can calculate the so many things, and this is another statistics based on the death rate, okay, from whatever, and they incorporate that into the design, and from this and that and so on, they come up with this concept, and you see that this is the formula that I mentioned early in the session. That is, we always make sure that the resistance side, after we reduce the strength based on some uncertainties, will always be greater than the load side, which we also increase to account for some uncertainty. That is LRFD in a nutshell. Okay? Any question, ladies and gentlemen? Am I going too fast? No? Okay. Good. All right. So this is the example of the load combination on the LRFD side. This is the US based. Okay, if you have the date load alone, you multiply with that, and you have the late load and live load, and this and that, and blah, 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 blah. Okay? And this is the reliability index that they incorporate into the column design. I'm not going to go into details about this. And that's more examples on the various LIFD combinations. The US, the Canada, and as I mentioned, here for our country, it's only available for concrete. We don't have that officially for steel. Okay? Now, it's pretty much the same for the ASD. It's based on the statistics, but the approach is simpler because you just take the load as it is, and then the resistance, you have that, and you just need to make sure that everything is safe, so we divide our resistance by factor of safety. It's pretty simple, okay? And yes, of course, the right side should always remain bigger than the left, okay? And this is the example of the load combination of the ASD. And, you know, it's pretty straightforward and simple really to just add them up. And, you know, let me ask you this. Some of you in this room, do you still use the ASD 89? Okay, some of you use it's nothing wrong, but, you know, there's one crazy, let's say, gap or loophole in ASD 89. That is the live load. The combination of the wind load, I'm sorry. Please don't do that. You distract me. Don't act like a villain, okay? You can do that, whatever, but just don't let me know about it, okay? Okay. ASD 89 would suggest that if you have the wind load in combination with the live load and the day load and everything, you can reduce the load by 25%, right? That is very dangerous because, first of all, the wind load, if you use the old one, it's on the, you know, underestimated side of the true wind load that occurs in Thailand. The wind load that actually occurs is stronger than the previous Building Act, and even with the new calculation based on the Department of Urban Planning standard, you may be on the underestimating side of the load. And now when you come in and you use ASD 89, it says you can reduce the load by 25%. So it's very dangerous. And I believe this may lead to many collapse structure. Right? The advertisement board, when they face a strong wind, they collapse because of this. You reduce the load. And the strength, I'm not sure, I don't remember, but they perhaps increase the strength somewhat as well. But this is for sure, they allow you to reduce the load. And that's not realistic. And see, we are engineers, we should know better. This underlines the fact that laws and suggestions from standards and specifications may not be correct all the time. It's just suggestion. You don't need to worship those things. You don't need to blindly follow those things. You are engineers. You need to make good judgment. Okay, so please keep that in mind. Okay, and yep, I think I have already mentioned that. That's the difference between ASD and LRFD. So that's a keyword that you need to use. Okay, that you need to know. I'm sorry. That's the load. We generally call it factored load because we use factor to say modify the load, magnify it a little bit, and the resistance side is reduced by the keyword here is the resistance factor. So if you know the right words, when you talk to foreigners, you use the right words, you have the common understanding and you can understand each other. Okay. And on the ASD, it's a working load, unfactored, or service load. Okay. That will be compared with the resistance, which will be reduced by the factor of safety. Okay. And some of you may already know this. Generally, there are two kinds of failure in steel. One is yielding, which is ductile. Ductile means that it's not gonna come down instantly. You know, it's just slowly coming down. And the perfect example of this is yielding. All right. So yielding is the ductile failure is less severe. Another one is the rupture failure. It's just if things just, you know, get torn apart from each other, and we call that rupture. A rupture failure is a brittle failure. It happens so quickly and suddenly and unexpectedly. So it's more dangerous. That means whenever you are dealing with the yielding, the reduction factor is only 0.9 and the factor of safety is only 5/3. But when you're dealing with rupture, which is more critical, more dangerous, the phi factor is less and the factor of safety is more. Okay, this just to reflect on the behavior of the structure based on failure. Okay, so you have yielding and rupture. We're not going to have more than that. We only have yielding and rupture in terms of strength. Okay, are we crystal clear? Yes, we are. Okay, excellent. So now on the new specification, which I think I already mentioned, we have the AISC, the latest version, and then we have the EIT, you know. But EIT is not up to AISC yet. And ladies and gentlemen, as I always underline, we use this to predict the strength of our structure, right? There's no guarantee that this will cover everything you do, because I went to the conference about steel structure yesterday. I have to say I was flabbergasted with the capabilities of engineering nowadays. Some of the things, the specification doesn't have the means for you to calculate for. For example, they use 3D printing to print the building. We use 2D printing to print the document, right? But now some can use 3D printing to print the hot dang building as a whole. So we no longer cast concrete, we print it. So and sometimes they can use 3D printing to print the steel connection with the shape I cannot explain in words. And there's no way we can calculate that by using specification. You can forget about it. The specification could never give you any formula for that because it looks so shapeless. It looks like a bush, you know, and it's, maybe I better quit my job while I'm ahead of the game, because one day may come that, okay, you guys cannot do anything about engineering anymore. Seriously. And you know, one thing I like to share yesterday that I was so shocked. You have been exposed to BIM, right? The building information, that kind of thing. Now they have some sort of virtual reality BIM. You know what that means? You guys, we have some sort of lens, you know, but for virtual reality, you will be locked in the virtual world. They call this mixed reality. And when you're wearing these special glasses, you can impose your drawings on the real structure like this. Can you imagine that? So if you have your drawings in these lenses, you can just look, okay, in the drawings we're supposed to have like 6 dB 20 here. So before you cast concrete, you look through the glasses, okay, 6 dB 20 on the drawings, or 6 dB 20, oh, that's correct. So we move on. It's that crazy now. So you have drawings, virtual drawings imposed on the real world. So for those who cannot catch up with the technology, you will be left behind one day, scratching your head, what the heck is this? I better start knowing virtual reality by playing PlayStation first, right? They have that virtual reality game. I cannot believe that. And the way you control the mixed reality, they just use some kind of gesture control, whoop, 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 like that. So it's no longer like Hollywood movies, ladies and gentlemen. It's here for real. I was really shocked. I still use hand calculation and design buildings. And they're doing things like this. So, but at least you know it by now. So keep in mind that we are not going to compete with technology. We cannot compete with robots. We cannot compete with computers. We learn how to use it. Okay? So where was I? Okay, anyway. So yeah, AISC 2015, that's the newest version. So if you really wish to use something up to date, I suggest you use AISC because EIT, they're working on it to try to catch up with AISC. And for the core form, we have AISI, and EIT also have that in Thai version as well. Now, I think I already mentioned that the AISC, the latest version, different from EIT standard. Okay, and now this is has been mentioned earlier that the AIC 2015 have the both ASD and LIFD unified in one. So you can just look at one set of formulas and you choose whether you want to use ASD or LIFD. You use the formula to calculate the nominal strength or the calculated strength, and then you choose ASD or LIFD. If you choose ASD, it means that you're going to use the service load and compare the service load with the calculated strength divided by factor of safety. Okay, and if you choose LIFD, it means that you're going to use the factored load and compare that with the calculated strength multiplied by reduction factor. Just like this, right? I have already wrote it down. So that's the whole concept. Okay? Let's come back here. Okay. And please don't get confused with this. If you mix up the two factors, you're gonna, wow, I don't know what to say. You're gonna, head down in the direction where you don't want to go. Okay. So for ASD, it's a factor of safety, and you divide your calculated strength with factor of safety. Okay. You don't multiply it, because factor of safety is always greater than 1, right? So if you multiply your calculated strength with factor of safety, you're increasing your number. And that's not nice, that's not safe. And if you use LRFD, you will multiply the factor with the calculated strength because it is always less than 1. So if you divide your calculated strength with the phi, which is less than 1, you're increasing it. So please be mindful, okay? Just mind the gap. Okay. And, all right, for example, this is where it is. If you look in the specification now, you see that they will give you one set of equations. And the subscript n is always there to tell you that this is the nominal strength or the calculated strength. You get whatever number from the formula that you use to approximate the strength of the structure. But before you can use it, you need to incorporate the reduction factor. And when you multiply the reduction factor with the nominal strength, this term becomes something we call design strength. The number that you can use in design, but that doesn't mean this is the number for designers only, right? Contractors and consultants can use it as well. It's just the design strength, the number that you can really use. If it is ASD, you will divide the nominal strength or the calculated number by factor of safety. And again, this becomes the design strength for ASD. So we are crystal clear on that, right? So now, from now on, we're going to just talk about it. And you guys will be able to handle this yourself. Okay? Now, the most important thing is the concept, ladies and gentlemen. Say if you mess up the calculation, chances are it's not going to be more than 5-10% error, right? But if you mess up the factors, that's huge. It's going to cause a lot more error than it's just a miscalculation in the formulas. Okay? And from my experience, the most horrible error is when you miss the load. Really, because on the strength side, the calculation or whatever you do, if you make a human error, generally it's like 5-10%, so on. But say if you miss the load on your structure, say you miss 1 point load, that could be like 50% error. And that, ladies and gentlemen, I'll see you in court, right? That's not nice. I met my senior yesterday. I was quite happy to just have met a senior from faculty engineering, who has been quite successful. And then, yeah, it just reminded me of something that I have always been told when I was a student, that you choose civil engineering, one leg is already in jail, the other is ready to follow. It's just waiting to follow in. So yeah, the load side is always the most critical one. Okay, and now I'm glad that we have we've got over the concept. So from now on, we can get into the technical side of things. Okay, now this is what's been mentioned already. From now on, the ASD 89, if you're in the US, has been superseded by the new specification. I guess there's nothing wrong if you want to stick to ASD 89, because as I always believe, it's the approximation. But I also believe that if you use the latest version, the new approximation that they give you should be better than the approximation that they gave you like 30 years ago, because time moves on, right? And that means if you work with some companies like top drawer companies, when they say you need to use the latest version to approximate the strength, and you use ASD 89, well, they're not gonna hear you. They will just refuse flat out. I want the latest version. So keep that in mind as well. Okay. And that's a change in details, and the details that change from the unification of the two design approaches will be, yes, some formulas will change, and there's some new things will be added as well. So with respect to ASD 89, things are not quite the same in some regards. Okay, so you need to keep that in mind. Let's say this is the old days. ASD 89 looks like that, right? Somehow the cursor is gone again. Can I maybe later. Okay? I'd rather just walk up and down because, you know, if you sit like 6 hours straight, you're gonna get a lot of gas here, and that's not nice. So you see, for those of you who are familiar with ASD 89, you're gonna see the form like this, and it's horrible because what unit is that? Foot, Pascal, kilogram per square centimeter? I don't know. But finally they got smart and then they removed the Young's modulus. I mean they incorporated the Young's modulus back into the square root. This is the latest version, right? The new ASD and the ARD. And you see the Young's modulus and the yield strength, they have the same unit. So this becomes unitless. So you need not worry about what unit you're on anymore if you use a new one, right? Isn't that better? Can become animated, just me. Otherwise I can go on. So for me, I don't need to memorize anymore what kind of unit I'm on here. So, truly speaking, I hate that. I like it. You can use kilogram per square centimeter, you can use megapascal, you can use foot. The number up front is the same because this just becomes unitless. Isn't that wonderful? Use the microphone all the time. Sorry about that. Okay. I'm used to not having a microphone because I like to scream a little bit. Okay? And the next one, for example, this is the combination, the comparison between the OASD. You just get this one formula, right? Again, I hate because it doesn't give me any idea what I'm dealing with. But the new one, it will give you the specific idea what things are going on, and we will get into more details about this. I just give you a glimpse of how things become different. Okay, and this, ladies and gentlemen, because I was taught ASD 89, but they never showed us this, right? This is the idea of ASD 89 on flexural strength of a beam. Generally, if the unbraced length is less than this, you get the allowable stress equal to 0.66 Fy. You know where it comes from? Right? And then after you pass one limit, a sudden drop of strength down to 0.6 Fy. This is the OASD. And then, this is what I love the most. When you're in this region, they give you like this, and that 3 equations, and calculate all of them and use the maximum number for your answer, right? Maximum number, are you kidding me? So my common sense tells me, how can we be safe if we use the maximum number? Why don't we use the minimum? Why? Because it's a curve fitting formulas. The maximum number would mean that it fits the curve better. But the teacher did not tell me that, back 30 years ago. So I was just, no, I can't believe it. And I messed up my undergrad steel design badly because of these 3 equations. But now, I don't care about that anymore because after the unification, we have a better set of equations that looks, it makes more sense to me. And we get to that later on. You have 3 distinctive regions based on the unbraced length, and the calculation looks far more simpler than this one, right? Just look at that. What the heck is that? But you have to admire their effort in the past because I believe that if you are used to ASD 89, some of the formulas are so crazy because they use that long before the invention of the calculator. Yes. So the calculator cannot I mean the slide rule, right? They use the slide rule. A slide rule cannot handle this. If you are going to use a slide rule to calculate that, say, okay, I'll see you next month. I'll design the beam for you, something like that. So it was not very practical, so to speak. So you have to admire their effort, but time moves on, you know, and so shall we. Anyway, and that is the formulas for the calculation of the LP and LR as well. Okay, so that is the end of the introduction, I suppose. So when is the break coming, Kun Tam? So let's start on the 10:30. All right, very well. So that's it. Any question, ladies and gentlemen? Okay, we're going strong. It's nice. Okay, so now that's it. That's the introduction. That's the concept. And those are my kids. And why? Okay, you gotta punch that up. Okay, button, so it comes on. So we're now gonna talk about, say, the details of the calculations now. So if any of you have any question regarding the concept, the unification of the design specifications and so on, please ask now so that you're clear and you're ready to go on to the next level. Wow, it's good, right? Everybody's just piece of cake. It's like that. Okay, so now, ladies and gentlemen, before I get into that, let me, because I like to talk about the big picture first, so that if we have the big picture right, if we have the concept right, the next thing is just easy. It's just to save some paper. Now, yeah, okay. Steel is a homogeneous material. We all know that, right? Steel. Let's say if I take the piece of steel like this, I apply tension. I keep increasing the load. It's gonna fail in some area. If it's tension, either it is going to yield, right? Or it is going to rupture. Right? Everybody can see that. It's pretty clear. If you keep pulling the steel, you know, at one point of time in time, it's gonna either it's gonna yield first. If I don't have anything specific, it's just one steel rod, and then it's gonna rupture. When the yield is going to occur, it's going to occur where the stress is labeled as Fy, or yield strength. We clear on that, right? Very, very crystal clear. If it's going to rupture, it's going to occur when the stress level is equal to the ultimate tensile strength that we call Fu. And I think, do I need to draw the stress-strain relationship? We have that in mind here already, right? Do you need it? You don't. Good. Oh, you do? No response? So I suppose you don't. Anyway. Now, if I, again, doing the same. But this time, as you may know, I apply compression. I can just keep pushing and pushing and pushing. If this rod is short, I can get to the point where the stress can be equal to yield strength. Am I correct? But you cannot squash steel just like concrete. If you take concrete cylinder and you apply compression, it's going to break. But what's going to happen to steel is that if you keep applying compression, it's going to buckle. right? It shouldn't sound like that. I just cannot think about the appropriate sound. So let's stick with the like that, okay? Actually, it should not have any sound. It's just gonna go sideways. It will lose stability. And that at that point, when the steel structure loses stability, the stress at that point is not known. Thank you, Director. We do not know, and we call the stress where we lose stability the F critical. So before we do anything, let's, have the common understanding that we need to know how much that is. The critical stress, the stress when the instability of the compression member occurs. Okay? And this, we have the behavior that we call buckling. A buckling means the material itself is not completely destroyed, but the structure becomes unstable. And we as engineers say, no, you can no longer use that. So the point is that we need to know how to approximate this critical buckling stress. So when your structure is under tension, it's straightforward. It's going to go to the strength of your material. But when it is under compression because of stability problem, you will not get to this. So F critical is generally less than Fy. Right? This is a common idea. Now the rest is about calculation. This is the general idea. If it's under tension, you can approximate the stress where the failure occurs right away, because the stress where the failure occurs is equal to the strength of the material itself. But when under compression, the stress where failure occurs is not the strength of the material. And that is why we need to come up with the method to approximate this stress. That is why we learn those crazy formulas. But the main purpose is just to estimate the stress where failure occurs. And this is the same for flexural member, but the flexural member you have more complicated stress, that's all, because the flexural stress has both tension and compression. So this becomes a more questionable approach. Okay? So now, this is the big picture. If we get the big picture, we will not be lost when we see a lot of calculations, because we know this is where we're going to go. Okay? Crystal clear again. Wow. I begin to feel quite confident. Okay, so that's it. All right. Now, as I already introduced to you, if it's a axial force member carrying tension, you will either reach the yield strength here, okay? And if this is a stress in the section, and because it's the axial force, that means you can easily calculate the tensile strength of your member by multiplying the yield strength with the area. Correct? This is the stress multiplied by the area, so you get the force. And this is the nominal strength. Okay? That means this is the calculated strength. Hello? Okay. Just gonna walk, just feel the pain in the back. Oh, okay. So this is the calculated strength of your member under tension. The yield strength multiplied by the gross area. If you want to approximate this and compare with the load by using ASD approach, you will divide this nominal strength by factor of safety and compare it with the service load. If you want to use the LRFD approach, you will use this nominal strength multiplied by the fee factor and compare with the factored load. Okay? Now, it gets a little bit more complicated because if you have holes, chances are the section where the holes are may rupture before this cross section yields because you have less area. You lose some area because you need to punch holes to connect members by the bolts, right? So we can have another possible failure mode, that is the rupture in the net section area, right? If you don't have holes, it's not gonna rupture before it yields because the ultimate strength is greater than the yield strength, and you have the same area, so it's gonna yield before it ruptures, definitely, right? But now when you have the holes, there is a possibility that this failure may occur somewhere here when you have holes. And we can approximate this failure because it is going to rupture, therefore it's the ultimate tensile strength. But the area that we use in our approximation becomes what we call the effective net area. Well, of course, it makes sense to use the net area because, there are holes in here. So you need to deduct the holes from your section. But there is also another phenomenon that may not allow you to reach the ultimate strength multiplied by the net area. So that is why we need to use the effective net area, which is the net area multiplied by the new factor that they call shear lag factor. Okay? Now, I don't know if I should talk about this today or I should wait until tomorrow because it is part of the connection. But if I have it here, let's talk about it right away. Okay?